Students, in this video we are going to discuss hydrogen spectrum. Here, how the spectrum are produced, like when the material like solid, liquid, gas or heated up, these material emit the electromagnetic radiation. When the material like solid, liquid gases are heated up, it is emit the electromagnetic radiation. So, for example, when the white light is examined through the spectrometer, the electromagnetic radiations of all wavelengths, are observed, which is a continuous spectrum. So, when the white light is observed by the spectrometer, here all the electromagnetic spectrum are observed, which is called continuous spectrum. Like for the hydrogen spectrum, when the hydrogen gas enclosed in a tube, this is a tube, glass tube, it is filled with the hydrogen gas. So when the hydrogen gas enclosed in a tube is heated up, it is emit the electromagnetic radiations of certain sharply defined characteristics of wavelength. This is called hydrogen emission spectrum. This spectrum is also shown in the figure. Okay, so this is one of the glass tube filled with the hydrogen gas. It is heated up by using the high voltage difference. It is heated up means it is emit the electromagnetic radiation. This electromagnetic radiation is also examined. Here it is produces a emission spectrum, that is hydrogen emission spectrum. Like when any gas is heated up, the thermal energy is supplied to excited the electron. Similarly, by all occurring light on the atom, electron can be excited. Okay, so in a hydrogen gas molecule, there is also having the atom, electron. So when it is heated up, these electrons are absorbed the energy, then it is jump from one stationary state to another state with those wavelength for the colors that are not observed or seen as a dark lines in the absorption spectrum. It is shown in the figure. Students, this is a diagram for the emission spectrum. For the emission spectrum, it is also emitted in different wavelength: violet, indigo, blue, green, yellow, orange, red, like this. This is one of the absorption spectrum. Okay, the electrons absorb the energy and it is produce a spectrum. In this spectrum, it is produce a dark line. Since the electrons in excited state have very small lifetime, the electrons present in the excited state, it has a very small lifetime. It is immediately jump from the excited state to ground state. During this transition, it is emit the spontaneous emission within the short duration of time. Here that time taken is approximately 10 power minus 8 seconds. Okay, friends, so the electrons present in atom, when it is heated up, it is reached to X-ray state. Here the lifetime in the X-ray state for the electron is very small. So immediately it is returned back to the ground state. So it takes time to return back to the ground state, that is 10 power minus 8 second. It is important. One more question, student. So during this transition, it emits the radiations with the same wavelength corresponding to the colors it absorbs. This is called emission spectroscopy. So the wavelength of these lines can be calculated with great precision. Further, the emitted radiations contain wavelength both lesser and greater than wavelength of the lines in the visible spectrum is given in the figure. Students, this is a spectral lines of hydrogen atom. In each series, the distance of separation between the consecutive wavelength, decreases from higher wavelength to lower wavelength, and also wavelength in each series approach a limiting value is known as the series limit. So this is a diagram for the series limit. Okay, so here this wavelength in each series, the distance of separation between the consecutive wavelength, like distance of separation between the consecutive wavelength decreases from higher wavelength to lower wavelength, and also wavelength in each series approach a limiting value. It has approaches limiting value is known as a series limit. These series are named as Lyman series, Balmer series, Paschen series, Brackett series, Beefan series, etc. So the wavelength of the spectral line perfectly agree with the wavelength calculated using equations derived from the Bohr atom model. By using the Bohr model of an atom, we can calculate 1 divided by lambda is equal to R into 1 divided by n square minus 1 divided by m square. So it is also equal to nu bar. Here this nu bar is known as a wave number. This is called a wave number. Nu bar is called a wave number. This is inverse of wavelength. Okay, it is equal to inverse of wavelength. Here the R is known as a Rydberg constant. It has a value is 1.09737 into 10 power 7 meter inverse, and M and n are the positive integers. Always the m is greater than the n. Okay, the m and n are the positive integers. Always the m is greater than the n. So now we are going to discuss the various spectral lines given in the hydrogen spectrum. The first one is Lyman series. For the Lyman series, here the n is equal to 1 and m is equal to 2, 3, 4 and so on. In equation, the wave number or wavelength of the spectral lines of Lyman series which lie in the ultraviolet radiation. The Lyman series, lies in the ultraviolet radiation. So the electrons are jumping from the energy level 2 to 1, 3 to 1, 4 to 1, 5 to 1. From the excited state, it is reached to the ground state from the various energy level. During this transition, it is emitting the Lyman series. Okay, so it is lies in ultraviolet region. So we can calculate the wave number. Nu bar is equal to 1 divided by lambda. It is also equal to R into 1 divided by n square. For the Lyman series, n is equal to 1. So 1 square minus 1 divided by m square. M means there is 2, 3, 4 and so on. Okay, in common we can write that is nu bar is equal to 1 divided by lambda is equal to R into 1 divided by 1 square minus 1 divided by m square. So next series, there is a Balmer series. So the Balmer series means the electrons are jump from third energy level to second energy level, fourth energy level to second energy level, fifth energy level to second energy level, sixth energy level to second energy level. During this transition, it is emitting the radiations like Balmer series. For the Balmer series, n is equal to 2 and m is equal to 3, 4, 5 and so on. So we can write the wave number or wavelength of the spectral lines of the Balmer series, which is lies in the visible region. That is a visible light. That is lies in the visible region. So the wave number nu bar is equal to 1 divided by lambda is equal to r into 1 divided by 2 square minus 1 divided by m square. So next one is Paschen series. So here for the Paschen series, here n is equal to 3, m is equal to 4, 5, 6 and so on. In equations, the wave number or wavelength of the spectral line, is lies in the infrared region. In electromagnetic radiation, it is lies in the infrared region. The wave number nu bar is equal to 1 divided by lambda, it is equal to r into 1 divided by 3 square minus 1 divided by m square. Next, bracket series. For bracket series, here n is equal to 4 and m is equal to 5, 6, 7 and so on. So here the wave numbers or wavelength of the spectral line. The wave number or wavelength of the spectral line is lies in the infrared region. That is middle of the infrared region. It is lies in the middle of the infrared regions in electromagnetic radiation. So we can write the wave number nu bar is equal to 1 divided by lambda is equal to r into 1 divided by n square, that is 4 square minus 1 divided by m square. So next, B-Fund series. For the P-Fund series, n is equal to 5, m is equal to 6, 7, 8 and so on. Here this wave number or wavelength of the spectral lines of P-Fund series, which is lies in infrared region. Here it is away at the infrared regions. It is far infrared regions. So here the wave number nu bar is equal to 1 divided by lambda, it is equal to r into 1 divided by 5 square minus 1 divided by m square. So this is the spectral series of hydrogen atom. Follow this question. I am going to teach limitation of Bohr atom model. It is important 3 more questions. So here the following are the drawbacks of the Bohr atom model. What are the drawbacks of the Bohr atom model? The first one, Bohr atom model is valid only for hydrogen atom or hydrogen like atoms, but not for the complex atom. Next point, here when the spectral lines are closely examined, individual lines of hydrogen spectrum are accompanied by a number of faint lines. Okay, so the spectral lines, it is also accompanied by a number of faint lines. This is called fine structure. Here this Bohr model of an atom, it is not explained, it is not deals about the fine structure of the spectrum. Okay, so here the faint lines are not explained by the Bohr model of an atom. Next, Bohr model of an atom failed to explain the intensity of variations of spectral line. Intensity variations of spectral line. The intensity variations of a spectral line, it is not explained by the Bohr model of an atom. Finally, the distribution of electron in various level cannot be completely explained by the Bohr's model of an atom. These are the drawback of the Bohr's model of an atom. Thank you, students.